So this section is about the first law of thermodynamics. Recall that thermodynamics is the science of heat and work. And to this point, we've only considered energy being transferred as heat. But now we'll need to broaden the discussion to include work. Work done by a system or on a system will also affect the energy in the system. If a system does work on its surroundings, energy must be expended by the system, and the system's energy will decrease. Conversely, if work is done by the surroundings on a system, the energy of the system will increase. So here is an example of a system doing work on its surroundings. So we have a small quantity of dry ice, which is solid CO2, put into a plastic bag and it's sealed. Then we have a book is placed on top of the bag, so a book has weight to it. When energy is transferred as heat from the surroundings to the dry ice changes from a solid to a gas. That's called sublimation. But in order for that to happen, energy has to be transferred as heat from the surroundings to the system. Now, as sublimation proceeds, gaseous CO2 expands within the plastic bag, lifting the book against the force of gravity. The system, which is the CO2 inside the bag, is expending energy to do this work. Even if the book had not been on top of the plastic bag, work would have been done by the expanding gas because the gas must push back the atmosphere when it expands. Instead of raising a book, the expanding gas moves part of the atmosphere. So now let's think about this example in terms of thermodynamics. First, we need to identify the system and the surroundings. The system is the CO2, initially as a solid and then later becomes a gas. The surrounding consists of objects that exchange energy with the system. This includes the plastic bag, the book, the tabletop, and the surrounding air. So sublimation requires energy, which is transferred as heat to the system from the surroundings. At the same time, the system does work on the surroundings by lifting the book. An energy balance for the system will include both quantities, energy transferred as heat and energy transferred as work. So, we are introducing the first law of thermodynamics, where we can say for any system, we can identify energy transferred both as heat and as work between the system and the surroundings. So we have our delta U, our internal energy, which is symbolized for U, as our heat and our work. We've shown heat as Q before, so energy transferred as heat to or from the system, and W is our new part to this, energy transferred as work to or from the system. So this is our main equation here, and this is written out. And so, like we said, sometimes expressed as the first law of thermodynamics. The energy change for a system, delta U, is the sum of the energy transferred as heat, Q, between the system and its surroundings, and the energy transferred as work, W, between the system and the surroundings. This equation defining the first law of thermodynamics is just a restatement of the general principle of conservation of energy. Because energy is conserved, we must be able to account for any change in the energy of the system. All energy transfers between a system and its surroundings occur by the processes of heat and work. So sometimes this equation states that the change in the energy of the system is exactly equal to the sum of the energy transfers from or to the surroundings. So we can see that the sign of U, heat transfer from the surroundings to the system, energy increases, its sign is positive. Work is done on the system by the surroundings, work is positive. Work is done whenever something is moved against an opposing force. Here's another just table showing sign conventions that are important. If heat's to the system, Q is greater than 0. Heat an exothermic reaction, Q is less than 0. Work done on the system, that means it's positive. Work done by the system, W is negative. And similar to what we just stated, that the energy change for a system, the sum of the energy transferred as heat between the system and its surroundings, and the energy transferred as work between the system and its surroundings. Remembering that energy cannot be created or destroyed, it is conserved and can be transferred between the system and the surroundings. The work in the example involving the sublimation of carbon dioxide is of a specific type of work called PV, or pressure volume work. It's the work associated with a change in volume that occurs against a resisting external pressure. So for a system in which the external pressure is constant, the value of PV work can be calculated by using this expression. To calculate this work in units of joules, the pressure is measured in pascals. And 1 pascal is equal to, so 1 pascal is equal to 1 kilogram / meters second squared. And the volume change is measured in cubic meters. Oops. To get a work in joules. In a constant volume process, when V is equal to 0, or delta V, when delta V, the change in volume, is equal to 0, that means that the energy transferred as work will also be 0, because anything that negative P times 0 would give me a work of 0. So the change in internal energy of the system under constant volume conditions is equal only to the energy transferred as heat, or Q. So if I go back and look at that equation, delta U is equal to Q plus W. If W is equal to 0, then delta U is just Q, because this would be 0. Therefore, the energy transferred as heat is going to be equal to that change in internal energy. Let's look at a couple of examples. So let's say we have nitrogen gas, 1.5 liters of it, is confined in a cylinder under constant atmospheric pressure. The gas expands to a volume, a new volume. So I started with VI, an initial volume. I have a VF, a final volume. When 882 joules of energy is transferred as heat from the surroundings to the gas, what is the change in internal energy of the gas? Well, first I want to find the change in volume of the gas. So let's, delta V is VF minus VI, final volume minus initial volume. So we're going to do 2.18 liters minus 1.50 liters, and we'll get a difference of 0.68 liters. Now, we need our volume, remember from our last slide, we need our volume to be in meters cubed. So we need to, for every 1,000 liters is equal to 1 meter cubed. So 0.68 divided by 1,000 is going to give us, I'm going to use scientific notation here. So take this divided by 1,000 6.8 times 10 to the negative 4 meters cubed. This is my delta V. Okay, next, the work is done by the system. So let's plug in our work is equal to negative P times delta volume. So what is my pressure? My pressure is 1.01 times 10 to the negative fifth, negative 1.01 times 10 to the, positive 10 times 10 to the fifth. In pascals, we said its unit, 1 Pascal is equal to kilograms meters second squared times delta V, 6.8 times 10 to the negative fourth meters cubed. So let's do that math here. I'm going to take my 6.8 times 10 to the negative fourth times 1.01 times 10 to the fifth. And then we're going to take that opposite of that. So work is equal to negative 68.68 joules. Now, finally, we can look at the change of internal energy. We know that delta U, the change in internal energy, is equal to Q plus W. So we were told that 882 joules of energy is transferred as heat. That's our Q. So 882 joules was my heat. Now let's add the work done that we just calculated, negative 68.68. So 882 plus negative 68.68. And we should get a delta U of 813.32. And if we think about this, the internal energy of a gas increases upon heating. However, the gas does not work on the surroundings as it expands against pressure, giving some of its energy to the surroundings. So we started off by finding the change in volume. We were told initial and final volume. We know that and the pressure, we can calculate work. Once we know work and we were given energy as heat, we were able to find delta U. Let's look at another example. Nitrogen gas is confined in a cylinder. We're given an initial volume under constant atmospheric pressure. The volume decreases to 2.1 liters when 485 joules of energy is transferred as heat, so that's my Q, to the surroundings. What is the change in internal energy of the gas? How about you pause this and you try to work through this one, and we'll check the answers in a minute. All right, well, hopefully, let's find our delta V. So our VF minus VI. We're going to take 2.10 liters minus 2.75 liters to get a delta V of negative 0.65 liters. Again, we need to change our units. 1,000 liters is equal to 1 cubic meter. So this is equal to 6.5 times 10 to the negative fourth meters cubed. All right, so this is our delta V. Let's plug that into our work. Work is equal to negative P delta V. We're given pressure 1.01 times 10 to the fifth pascals. And we know that that Pascal is equal to kilograms meters second squared. And that's a negative in front of that. And our volume, oh, I forgot to carry over our volume. This was a negative 0.65. This should be negative 6.5 times 10 to the negative fourth meters cubed. So let's do this math. I'm going to do negative 6.5 times 10 to the negative fourth times 1.01 times 10 to the fifth. And you take the opposite of that. So for work, you get a positive 65.65 joules. And so work is done on the system by the surroundings. So it's positive. So to find our delta U, that's equal to our Q plus W. Our Q, we were told, was 485 joules of energy. Our work, 65, instead it was, and here we go, it was transferred as heat to the surroundings. We know that if it is going to the surroundings, it is giving off heat. Therefore, Q is negative. It's an exothermic reaction if it is giving off heat to the surroundings. That is very important. Our Q is negative 485. And our W, we're just going to transfer this down here, 65.65 joules. So our delta U is negative 485 plus 65.65. We should get negative 419.35 joules. Right. Really the biggest one there was that this 485 joules of energy transferred as heat to the surroundings versus this one was 882 joules of energy is transferred as heat from the surroundings. That means that it is absorbing. That's why our Q is positive. Absorbing is endothermic, and that's a positive heat. If it is transferring as heat to the surroundings, that means that it is giving off heat. So that is a negative exothermic value. That leads us right into our next thermodynamic function called enthalpy, H. Now, H is our heat content of a chemical reaction. So most experiments in a chemical laboratory are carried out in beakers or flasks open to the environment, where the external pressure is constant. Similarly, chemical processes that occur in living systems are open to the atmosphere. Because so many processes in chemistry and biology are carried out under conditions of constant pressure, it's useful to have a specific measure of the energy transferred as heat under this circumstance. So again, remember, under conditions of constant pressure, we use the equation of delta U, right up here, delta U is equal to Q plus W, where the subscript P indicates conditions of constant pressure. So this would be QP, WP, again, constant pressure. If the only type of work that occurs is pressure volume work, then we know that we can write this as delta U is equal to heat, Q, at constant pressure, minus P, right? That's what our work, we just sub in there, is negative P, V. If we arrange this to solve for Q, if we want to get this on our side, we got to rearrange this equation. We would get Q is equal to delta U plus PV, right? I just need to add PV to both sides to have Q by itself. Now, enthalpy, H, is defined, we're just taking Q under constant pressure, and we have just redefined this as H. H is equal to U plus PV. Enthalpy is the change in enthalpy for a system at constant pressure would be calculated. I said the change is just delta H. So that is the change in U plus P times delta V. Again, triangle V in front of there. That would be the change. So delta H is equal to QP. So we said, wait a second, I thought Q was the heat of a reaction. Well, yeah, it is. We can say the change of enthalpy is the heat flow, Q is equal to delta H. So for a system where the only type of work possible is PV work, the change in enthalpy, delta H, is equal to the energy transferred as heat at constant pressure. Now the directionality of energy transfer is indicated by the sign of delta H. So that those two reactions that we just looked at, negative values of delta H means that energy is transferred as heat from the system to the surroundings, and it's exothermic. I'm going to erase these real quick and write that. So negative delta H values means it's exothermic, and that means that energy is transferred as heat from the system to surroundings. I'm abbreviating here. And if we have a positive delta H, that means that we have an endothermic reaction, or an endothermic process, and that heat is transferred from the surroundings to the system. Here's another chart to just kind of show us. If we have an exothermic reaction, so again, remember, exothermic reaction is when we have heat and energy being transferred from the system to the surroundings. So the surroundings warms up, right? Because heat is being expelled from the system, so we feel warmth. Versus endothermic, when we have surroundings heat transferred to the system, so the surroundings cools. Our delta H is negative in an exothermic, delta H is positive in an endothermic. The effect on the system, so E is subtracted, energy is subtracted from the system. Again, because in an exothermic reaction, energy is transferring from the system to the surroundings, so the system is losing energy, right? And in an endothermic reaction, the system is gaining energy because the surroundings is losing energy. And this brings us to our last part of our section. It's about state functions. So internal energy and enthalpy share a significant characteristic. Namely, changes in these quantities depend only on the initial and the final states. They do not depend on the path taken on going from the initial state to the final state. No matter how you go from reactants to products in a reaction, the values of delta H and delta U are always the same. A quantity that has this property is called a state function. So again, we only care about the initial and the final states of that, not on the path taken. For example, here we go. State functions are independent of the path. Oops. Some examples. So let's say that I wanted to get from, here we go, from Dayton to Los Angeles. And I went from Dayton to Atlanta to Salt Lake City to San Francisco to Los Angeles. So my pink arrow just went direct flight. My green arrow took 1, 2, 3, 4 legs to get there. So what is not a state function? How long it took to get there, right? Obviously this took a lot longer, the time. The distance to drive, a lot longer distance. A state function of this trip would be the change in elevation, right? Start to finish, same change in elevation. same change in latitude. They're still getting from the same point. It's still the same delta, delta elevation, delta latitude. They're still getting from point A to point B. Doesn't matter the path that they're taking. So many commonly measured quantities, such as the pressure of a gas, the volume of a gas or liquid, the temperature of a substance, are all state functions. For example, if the final temperature of a substance is 75 degrees and its initial temperature was 25, the change in temperature, delta T, is just final minus initial, so 75 minus 25 to give us 50. It doesn't matter if the substance was heated directly from 25 to 75, or if the substance was heated from 25 to 95 and then cooled to 75. The overall change in temperature is still 50 degrees. Not all quantities are state functions, though. Some depend on the pathway to get from initial conditions to final conditions. Like that last example, if I said, what is the distance traveled from Dayton, Ohio to Los Angeles, California? The travel distance depends on the route taken, nor is the elapsed time, like we just said, the time to drive it. If I said between these two, obviously these two different paths would have much difference in time. But the change in altitude, and going from one place to the other, there is an altitude of a certain amount that's going to be the same.